Okay, so I want to look at some more kinds of problems that deal with three-dimensional vectors. And we can take the dot product really of any dimension vector, whether it's a 2 by 2 or 3 by 3, or actually for those of you who go into linear algebra, like 4 by 4 or 5 by 5. And that dot product, when you multiply those components, gives you a scalar value. Okay, it's not a vector. Okay, I'm going to define a new kind of multiplication called a cross product. And this cross product will give us actually a vector quantity. The thing about cross product, and the reason we haven't seen it yet, is simply because it only is defined for dimensions 3 and higher. So you need at least 3 components, like an I, J, and a K. And of course, in my head, I'm thinking, not joking, like I, J, K. No, I'm serious, right? But those are the letters. So it has to have 3 dimensions or greater. And we're just going to do 3 dimensions in this class. And if you do go into linear algebra, you would apply this to 4th dimensions, 5 dimensions, and up to the nth dimension. Now, cross product is distinguished from a dot product very, I think very literally, because the multiplication symbol is a cross. It is not a dot. And so that's how you know if I'm looking for a cross product between 2 vectors, it's going to be this particular process. And it looks a little intimidating, and it sort of is until you kind of get into the logistics of it. Then it's not too bad. It's actually based on determinants. And if you take a look, the vector U has 3 components, like the I, J, and K, which is like subscripted 1, 2, and 3. And then the V is also 3 components, and those coefficients are also subscripted 1, 2, 3. So if you take a look at this actually is a 2 by 2 matrix, and those symbols mean determinant. And of course, all my lemonade mouth fans are thinking like determinate. That's what's in my head right now. But like the determinant, notice for the I, which is the first position, notice the coefficients missing are the first position coefficients. And then the J, that's the second position. Notice the subscripts 2 are missing, and that's the coefficients of the J are missing. And then K is the third position, and notice that those correspondingly are missing as well. The other thing you need to notice is that the J is always the opposite coefficient. And the thing is that there's a proof here, and we're not going to prove it in this video, but for the nth dimension, they just alternate positive, negative, positive, negative, positive, negative. So the first one is it's whatever the value is. The second one is its opposite. Third one is the positive or whatever it is. The fourth one would be its opposite. So if we were to have extended this, it would alternate, but for us, that J component is always the opposite of the determinant that you get. And then one last quick reminder about how do you find determinants. Remember, you multiply down the diagonal, and then you subtract that distance, or subtract that product. Okay. So, but like that's the formal definition of the book, probably shows. I'll show you kind of how I work through a problem. So, and kind of see if this makes sense. So it says find the cross product U cross V. So I'm looking for a cross product. So I know it's going to be a vector between these 2 3-dimensional vectors. So what I'm going to do is I'm actually going to line them up in a 2 by 3 matrix. And it doesn't matter which one you put in the first row. So I'm going to put the coefficients here, 1, 2, -2. And then I'm going to put the coefficients 3, 0, 1. Okay. And then the way I like to do this is that since I know that the first matrix up here has no I components or no first column components, I'm sort of going to just ignore. I'm going to take my highlighter and there. I'm going to ignore that first column. And so pretend you don't see that first column. And in fact, maybe I can even make it so you don't see it. I want to pick a different highlight color, like really dark. Okay, so we're ignoring that first column. Now find the determinant. You have a 2 by 2 matrix. Remember, you can only find determinants of 2 by 2 matrices. So I'm going to go down this. 2 times 1 is 2 minus 0. So I'm going to get 2 minus 0. That's going to be my coefficient of the first matrix. So 2 minus 0, okay, which is 2. So I know that the coefficient of, so U cross V is going to be a 2I. Now, I always remind myself to put a minus there so that I know it's the opposite value. Okay, so then we're going to do the J. And so let's see, let me just come back over here. I don't know how to do this nicely other than just erasing. So we'll erase this and we'll just, just erase that. I gotta find a better way to do this. So this was 1, 2, -2, and this was 3, 0, 1. Okay, so now what I'm going to do is I'm going to take this and block out that second column. Well, that didn't quite work. Okay, so let's try that again. Let's cut that. And let's go to highlight. And oh, good, I already picked a color. Let's take out that column. Okay, so now again, I still have a 2x2 matrix. Now, there's no reason why you can't just keep rewriting these, but I kind of like just mentally block those out. And when you get good at it, you don't even have to like physically block it out. You could just mentally block it out. So I'm going to go down. Maybe pick yellow-ish. 1 times 1 minus -2 times 3. So 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 that's 1 basically minus -6, which is equal to 7. But remember, it is its opposite value. So since 7 was the determinant, I know it's an opposite of 7 there. Okay, let's see if this worked. I'm going to slide this over. Ah, beautiful. So now to get the K value, notice I'm only having component 1 and 2, 1 and 2, and that's what it says up here, 1 and 2, 1 and 2. So now I would do, so now I would do 1 times 0 minus 2 times 3. So 1 times 0 minus 2 times 3. So 0 minus 6 or -6. So that's my last component. So 2i minus 7j minus 6k. So this is the cross product. Now, one thing that I really like about the cross product, and it's sort of like the application that a lot of the homework problems are going to be based on, is that if you do the cross product correctly, this vector, oops, my bad, that vector that you get, okay, so sorry about that. I think I got that fixed. I restarted that, so apologize for the weird transition. Hopefully I won't have to again. So, where I last left off, we found this vector. So 2i minus 7j minus 6k. And it is a vector. And one of the things that is an application of that vector is that if done correctly, the cross product, which we just found, right? Remember, and the cross product is a vector. Excuse me, that cross product will be a vector that's perpendicular. Oops, I'm going to pick a different thing. So there you go. It's perpendicular to both given vectors. Okay, and if you remember from last week, it's really easy to check if it's perpendicular, because if it's perpendicular, remember then the dot product, not the cross product, but the dot product will equal 0. And so what I'm going to do is I'm going to look at this vector. So let's check my work, okay? And you don't always have to do this, but I do want to show this because it's a great way to check work. So I'm going to take vector I plus 2j minus 2k, and I'm going to look at my new vector, 2i minus 7j minus 6k. Remember, dot product, you look at the coefficient, so you multiply, so 1 times 2, so 1 times 2 plus 2 times -7, which is -14, plus -2 times -6, which is 12. So you get 2, that's the worst looking 2 I've ever seen. 2 minus 14 plus 12, which is equal to 0. So I know that the vector I just found is perpendicular to one of the vectors. Now, it probably should also be perpendicular to the other one, but just so, for good measure, I could sleep tonight. Take that other vector, 3i plus 0j plus k, and take our vector that we're claiming is a cross product, 2i minus 7j minus 6k. And if I multiply those, so 3 times 2 is 6, 0 times negative 7 is 0, and then 1 times negative 6 is negative 6. So yeah, it works out. So that's a huge application. It's perpendicular to both given vectors. And what I want to do is actually insert another example here. So either on a piece of scratch paper or maybe a notebook paper, what I want us to do is do one more practice question before I go back there. Here's another way I can ask you to find a cross product, right? It says find a vector that's perpendicular to both these vectors. So if you see, if you see a problem like this, where it's basically indirectly saying find the cross product, because the cross product will generate you a vector that is perpendicular to both. And it's kind of a cool thing, because if you think about this three-dimensional vector, you could have like a vector going in one direction and maybe another vector going in this direction, and somehow coming off the page, like in that third dimension, you're finding a vector that's perpendicular to both. This is where it'd be nice to have, like, physically you could see, you take two pencils and put them end to end, and then put a third pencil at the top of it, and that's your vector that's perpendicular to both. So let's go ahead and just practice that. And if you want to practice the algorithm without me and then see if you get the right answer, that's a great thing. Pause the video. Otherwise, what I'm going to do is I'm going to put this into a 2x3 matrix. And again, it doesn't matter the order. So 2, negative 5, 1. So 2, negative 5, 1. And then negative 1, 3, 3. So there's that first, so it's 2, negative 5, 1. Negative 1, 3, 3. Excellent. And then again, you're going to think about, if I go to highlight and I pick a darker color like this, so you're just gonna sort of ignore that first row, the first column, and find the determinant of the remaining square matrix. So I'm gonna have negative 5. Go to my pen here. And let's pick green. Okay, so negative 5 times 3 is negative 15 minus 3. So negative 15 minus 3 is negative 18. That'll be the I component. Remember, the J component is always its opposite. So then I'm going to hide this, and I have 2 times 3 is 6 minus a negative 1. So 6 minus negative 1, so it'd be 6. Really plus 1, which is 7. So then back to my pen. Excellent. So it's the opposite of 7. That's kind of ironic, because that was the same thing as our last vector. And then we do our last column. So 6 minus 5, because that's a positive 5. So 6 minus 5, which is 1. So I get plus k. So here's my vector that I'm claiming to be perpendicular to both. It's a vector that I can check very easily by doing cross product. So if I check the cross product, red. So if I had 2i minus 5j plus k, that was our first given vector, and I say negative 18i minus 7j plus k, let's do the dot product. Remember, the dot product gives us just a scalar, just a constant number. So 2 times negative 18 is negative 36. Negative 5 times negative 7 is positive 35. And then 1 times 1 is 1. So that would definitely generate a vector that's equal to 0. Or sorry, a value that's equal to 0. So most likely we did it right. But just again, so you could check the other one. Go this color. So we take our second vector, negative I plus 3j plus 3k, and we take our negative 18i minus 7j plus k, and let's find the product as a dot product. So negative 1 times negative 18 is 18. 3 times negative 7 is negative 21 plus 3. And again, we get 0, so we did it right. So it's a great way to check. That vector is perpendicular to both vectors. Okay, so cross product is a vector. Cross product gives you a vector that's perpendicular to both of your given vectors. And remember, the cross product is only defined in the third dimension or higher, which is why we haven't done that yet up until this point. So, okay, so kind of similar to the other learning modules. So now you have just a quick practice question, and then we'll look at some more applications of the cross product.